All right, good morning. I'm Dr. Wu. I'll be the person that's going to be standing up here talking at you about things that you're probably not particularly interested in for the next 3 months. Sounds like a long time, doesn't it? Hopefully, by the end, we'll have some fun and you'll enjoy it. But to get started, we do have some kind of boring things to get through to begin with, and that's just going to be going over the syllabus. But I promise we'll get into some more interesting things as we go. So the syllabus should be making its way around right now. All of the course material is going to be available on the Blackboard page, so the syllabus is up there, as well as my lecture notes. So to start looking at the top, our course outline. So this course is going to be based primarily on Maxwell's equations and all of the equations that are related to them. So we'll start today, towards the end, talking about Coulombs Law. Next week, we'll talk about the electric field and electric potential. Then we'll get into flux, Gauss's law, capacitors, resistors, time, dependent and independent circuits, the Lorentz force law, the Biot-Savart law, Ampere's law, Faraday's law, and the wave properties of light. The wave properties of light is very nice kind of capstone to all of this, because all of Maxwell's equations build into the way that we can describe light ultimately. So prerequisites for this course, hopefully you've taken Physics 2001. You should also have taken Calculus 1 and 2. For the course materials, the only required text for the class is going to be my notes. Okay, so I already have these posted for this week on Blackboard. I sent them out yesterday. Additionally, I'm going to be posting a lot of things on YouTube. You see that I'm recording the lecture right now. You can find my YouTube channel by going to Wu Physics 87, or just searching Wu Physics 87 on Google. So what will I be posting here? Well, I'll be posting the videos based on my lecture notes. I posted one this morning for Coulombs Law. I'm going to be posting these videos of our lectures, and I'm also going to be doing a weekly live stream on Mondays, or I might change that to Sunday, depending on what my scheduling is like. So during those live streams, it's an open forum. Any questions that you guys have about the class, I'll answer and go over the material. So additional resources that you'll have. So when studying for exams, who likes having practice exams? Yeah, everybody likes practice exams. Well, I have the mother lode of practice exams. So if you click on this link from the syllabus, this is 12 years worth of exams. In fact, I won't tell you what year it was that I took this course, but the year that I was in this course is on here as well. So there's going to be a lot of practice exams for you guys to go through, and they also have the answers to them as well. Not complete solutions, but if you click on one of these, you see you have the answers. And these, as far as the way that I'm going to be writing the tests, are basically identical to the way that I'm going to write the test. So the exams are going to be 4 questions, no calculator, no exam, no cheat sheet or equation sheet other than the information that's given on the front of the page, and it's going to be 4 open-ended questions like this. Now that might at the outset seem a little bit scary, but when I say that you can't use a calculator, it's because you don't need a calculator. None of the things that we're going to do in class are actually going to require using a calculator. Okay, so that's the exam repository. Additional resources. I created a Slack channel for the class. So who's used Slack before? A couple of you. So primarily what I want to use this for, I'm not going to answer questions via email. So if you have a question, post it on the Slack channel, because more than likely, somebody else probably has that same question. So it's good that somebody asks the question, and if I reply to it, then everybody can see that reply. But also, you'll be able to answer each other's questions. If somebody asks a question and you know the answer to it, then that's a good opportunity for you to work on explaining your answer, because ultimately that's what a lot of the exams are going to be about, is explaining how did I get from this point to this point. It's good practice. So there's a link in here for the Slack channel, so you can, when you go to Blackboard and click that. So the way that I have this set up right now is there's a channel specifically for homework help, and then I also made a channel for finding people to study with. Okay, so if you're trying to find a group of people to study with, or you want to try to organize with people in class to work on some of the practice exams, this is a good place to do that. Okay, next up, the textbook. So like I said, there's not a required textbook. The textbook that you used for Physics 1 has this material in it, so that's a good reference for you. But if you haven't bought that, or if you hadn't taken Physics 1 here or in a while, you don't actually need it. Now the second textbook is actually the textbook that I learned from, and is a very strong influence on the way that I think about the material and the way that I write my notes and the way that I'm going to teach it. And that's the Don't Panic Volume 2 by Bill Bassigus. Okay, office hours are going to be Monday, Wednesday, and Thursday, right after class. So if you have questions, just kind of come with me back to my office. I'll also make office hours by appointment if you have something else that you want to talk to me outside of the times that I've designated here. You can email me, and we can find a time to talk. Okay, so getting into the grading policy, homework is going to be 25% of the grade, classwork is 20%, each midterm is 15%, and the final exam is 25%. So some things to keep in mind here. There's going to be homework and classwork every day. I already passed out the first homework. That's going to do the next class at the beginning of class. And you see, looking at it, you might not really know how to do it yet because I haven't talked to you guys about the material, and you might not have looked at the notes yet, but it's short. I don't expect the homework to take you more than half an hour, 45 minutes at most. So there is going to be homework due every day, but I'm specifically writing it in a way that shouldn't take you a lot of time to do. Okay, so I'll talk about the homework and classwork policy when I get down to the makeup stuff. So there's also some available extra credit on the midterms, and that's by doing an exam correction. So when I say exam correction, what I want you to do is to go through your exam and look at where you lost points, and then determine what it was that you were thinking when you did that, and how that's different than the correct answer. And if you write that up, you'll be able to get 5 extra points back on each exam, up to a maximum of 100%. Okay. Grade distributions. Now, I already talked to a couple of students about this. I did specifically set this so that it was high for 2 reasons, really. So the A range is 100 to a 94, and the A minus range is a 93.9 to a 90. One of the reasons why I did that is because I want to set high goals for you guys to work on. The other reason is I want to set high goals for myself. So if I set a goal at 85, then that's less work in a sense that I have to do to get you guys to get there. But I want you guys to learn and understand this material. And so in setting these grade distributions, I'm keeping both you and I in mind, because it motivates me to try to help you attain these goals. Now, that being said, these are not set in stone, and if I find over the course of the semester I'm actually bad at my job and you guys aren't able to get here, then I'm going to lower these thresholds. Okay. So the makeup policy, basically there is none. I don't take late work for homework, but what I do is I drop the lowest 3 homework grades and the 3 lowest in-class grades. Okay. So part of the reason, and that might seem harsh, but part of the reason why I do that is it actually takes quite a bit of time to go back and grade things, and that's time that takes away from writing material for class. It takes away time from talking to you guys about the material that we're working on, and so really having a policy that lets you guys turn things in whenever you really want to is actually kind of bad for the class as a whole. Okay, so exam dates are listed here. So the first exam is going to be on Monday, June 4th. The second midterm is going to be Monday, July 2nd. Did you not get a syllabus? No. Okay, there's still some floating around somewhere? Okay, you got any extras? Yeah. Okay, thanks. Everybody's got the homework too? Okay, okay, you need both? Yeah. Okay, there you go. Thank you. Yep.
Thank you.
Okay. Yep, you guys too. I might not have a note. Okay. This is homework. Yep. All right. Anybody else need one? Okay. Yeah. Okay. Got the last homework. Exactly the number that I needed. You need one too? Okay. Are there any more of the homeworks floating around somewhere? Okay. Yeah, there's some. Can you just have those make their way down here? I don't want to spend too much time passing papers out. Okay. All right. So, I haven't figured out when the final exam is going to be. These two midterms are going to be in class, so they're going to be Monday classes, so like today. The final exam we're going to do, like I said, I haven't decided exactly how I want to do that. I think what I'm probably going to do is I'm going to give the final exam over 2 days because the 1 hour's not long enough to do that. There's a statement about the Americans with Disabilities Act here. If you're somebody that needs extra time on exams or additional accommodations, make sure that you contact the office of the Accessibility Resources Office, and we'll work with you on that. So. At the bottom here, and this is actually going to just be our classwork for today, put your name and sign that you read and understood the syllabus, and you can pass those to the front. I'll return these on Wednesday so that you have a hard copy. All right, so getting into the real material for today, I kind of want to talk about my personal philosophy when it comes to this class, and basically rant at you for 3 different topics here if you've looked at the notes so far. So the first rant, it has to do with the way that mathematics is taught and the way that you've probably learned calculus. So by a show of hands, who's taken Cal 1? Cal 2? Cal 3? A couple people take Cal 3. You don't need Cal 3 for this, but something that I'll make it as an aside for you is the type of calculations I'll have you do in Cal 3 I think are kind of silly. But when you take calculus, at least when I took calculus, learning calculus really meant you have this giant list of derivatives for a worksheet. Do all of these derivatives. You have this giant list of integrals. Do all of these integrals. And then you're proficient in calculus. I give you like a list of functions, integrate this. And the issue with that is it doesn't quite get at the root of why are we doing this in the first place? What is calculus good for? So that's one thing that I want to address in this class. The second thing, and partly why I'm writing my own notes here, has to do with the way that physics books are written. So who enjoyed the book from last semester? Nobody? I thumbed through it a bit myself, and I don't think I probably would have enjoyed it either. But the issue with those books personally is that they tend to be more of a compendium of equations, right? Here's a whole list of equations. Here's a couple of situations to use them for, and then we'll throw some calculus in there for certain problems, and then that's calculus-based physics. It's basically algebra-based physics with a little bit of calculus and slightly harder problems. So that's another thing that I want to address. The third thing, and this is just a personal pet peeve of mine, is when people say something is just a theory. So as a scientist, theory means something very specific. In physics in particular, theory has three important cruxes. The first is that it's experimentally testable and falsifiable. So if you come up with a theory and there's an experiment that somebody performs that gives you results that are inconsistent with the theory, you have to go back to the drawing board. It doesn't work. The second thing is that theory can make predictions. So historically, when Newton came up with his law of gravitation, the famous prediction that he made was when Halley's Comet was going to come back. And he was able to predict that it was going to be about 70 years before it comes back. So theory can make predictions. And the third thing is that theory can reproduce results of an old theory. So we're going to see that when we get to Gauss's law. That's going to recover the results of Coulombs Law. So when somebody says, I have a theory about what Donald Trump's hair is made out of, it annoys me because it's like that's not really what theory is. That's an idea or a supposition, perhaps. So in designing this course, I wanted to address those three things. And so really what we're going to be doing is we're going to be using calculus to prove physics. So in the process, you're going to be able to understand what is calculus good for in the first place, where does the physics come from, and then the third part of that, my discussion about theory, is you're really going to be able to understand what it is exactly a theoretical physicist does. They don't sit in their office and just ponder and come up with ideas. They prove things and draw connections between things. Okay, so to give you something to look forward to and a general equation that is basically everything that we're going to see in the entire semester in integral form. The integral of stuff, from stuff to things, of something, d something else, is going to be equal to different stuff. I wrote it a little bit differently here. So this might seem like kind of a silly thing to do here, but the point that I'm trying to make is that in looking at all of these equations that we're going to see in physics, every single piece of any given equation we're going to have has meaning. And we're going to understand both the physics and the calculus in a deeper way when we pick these apart and when we see what it is that we're doing with each piece here. Okay. So the next thing that I want to do is I want to give a little bit of a review or kind of a slightly different way to think about calculus, because at least when I took calculus, it was really beat into me that an integral is the area under a curve, right? You've probably heard that a lot, and it's true in some circumstances, but an integral is a lot more than just the area under the curve. An integral is actually just a fancy way to add tiny little pieces up, and the area under the curve is just an example of that. So to start with, and to give you some idea of the way that I'm going to be using notation here, let's talk about how we can find what the length of some line is. If I say that this is some position A and this is some position B, and I have some line that extends from A to B. So you might think that, yeah, this is easy, right? You just say that the length of this line is going to be B minus A. But we can talk about this in the context of calculus. If what we do is we say, okay, well, for this line that I have here, let me consider breaking it up into tiny little pieces, call them some dl. And if I want to find what the total length of this line line is. All that means is I need to add up all of the tiny little pieces of DL along the portion of the x-axis where the line exists. So in the language of calculus, what this says is that the total length is going to be equal to the integral of these tiny little pieces of length starting from where the line begins going to where the line ends. Okay? And this equation I've written in a very general form, some DL. DL could be some arbitrary tiny little piece of length. It doesn't have to be along the x-axis. It could be along the y-axis. It could be along the arc of a circle. It could be along something more complicated like a parabola. But this equation is going to be true in general because all it says is take all the little pieces, parameterize what DL is, and then add all of them up over the boundaries, and that's going to give you the total length of the line. And so for this example, what I can say is that DL is going to be equal to dx, right? This is the x-axis. This is the y-axis. And so this DL here is going to be equal to dx, and I'm going to add all of those little pieces of dx from A to B. So in this case, L is equal to the integral from A to B dx, which gives us our expected answer that this is just going to be B minus A when we do the integral. Okay. Now, again, you might say, well, this is kind of a silly thing to do. Why are we doing this? Well, let's look at another example of how we can add up tiny little pieces along some length to get us a result that we actually already know. So consider, instead of just having this segment of line to be along the x-axis, what if I wrap it around and I put it on a circle? So now what I'm going to have is some DL here. I always start by saying I have some tiny infinitesimal piece of length. Some DL that's along the arc of the circle. Now if this circle has some radius of r, then this DL is going to be equal to r times d theta. Okay? Now we can set up the same equation that we had before. We say that the total length is going to be equal to the integral from where the line begins to where it ends of DL. So that says that this is going to be L is equal to the integral DL, which is equal to L1, L2, which is equal to the integral of R d theta. Now looking at this, we see that the variable of integration here is going to be the angle theta. So that tells me what my boundary should be, right? So where should theta start and where should theta end? 0 to 2 pi, right? So this goes from 0, goes to 2 pi, right? So this is theta is equal to 0, theta is equal to 2 pi. So we start here, we go all the way around the circle, and we come back here. Now let's do this integral. This is going to be equal to 2 pi times r. Okay? And that's the famous equation that we have for the circumference of a circle. Now, we can generalize this idea of adding little pieces up to find some larger piece to talk about areas and volumes as well. So if we want to talk about doing this for some area, let's show how we can find what the area of some box is going to be. So the equation to find the total area is going to be very similar. So this is the total area is going to be equal to the integral of some tiny little piece of area. And what I'm going to do is I'm going to say this is over what the total area is. Now consider some box that I have here, where this is going to be some y is equal to c, this is going to be a, and this is going to be b. So we want to find what the area of the box is here. And the way that we can do that is we can say, well, we have all of these tiny little dAs that make up this box, where the dA, because it's an area is dimensionally what is an area? dimensionally, what's a length? Or what's the SI unit for length? Meter, right? So what would the SI unit for area be? Meters squared, right? So here, when I say there's some dA, really this needs to be made up of two pieces, right, that are going to be multiplied together, two lengths. And so what we see here is we have some infinitesimal length in x, there's going to be some dx, and some infinitesimal length in y, dy. Okay? So for this example, what this says is dA is going to be equal to dx dy. And now to find what the total area of our box is, all we need to do is we need to plug this dA into our integral. So this is going to be dx dy. And actually now, because I have a dx dy, this becomes a double integral, right? I have two variables integration. I need to do two integrals. And so then we need to ask ourselves, well, where does x start, where does it end? X starts at A, so x goes from A, and it goes to B. So this goes from x is equal to A to x is equal to B. Y goes from 0 to C. Y equals 0, Y equals C. Okay, and then we just need to do the integral here. Now, if you haven't seen double integrals before, that's okay. I'm not going to explicitly have you do any of these. This is really just kind of to prove a point about the way that you can make big objects out of adding up the little pieces. But the way that you're going to deal with this is you're just going to do it one by one. So the first one I can do is the integral of dx from a to b. That's going to give me a b minus a. And then this is going to be a dy. Integral from y is equal to 0 to y is equal to c. And then when I do this integral, what I end up finding is this is going to be c times b minus a. Okay. And again, this is what we expect. It's kind of a trivial example, right? We know how to find what the area of rectangles is, and just looking at this, we should say, well, it's just going to be this length times this length. And we were able to prove that by doing this with calculus. We can also do this with a circle. Again, we could find what the area of a circle is. In that case, and I'll leave this as an exercise for you. If dA is going to be equal to r dr d theta, then we can show that the area of a circle is going to be pi r squared. We can generalize this even more to say, I can do this with volumes, right? So if I had some, if I extrude this out into the z direction, so that there's going to be some volume here, well then what I would say is that dv is just going to be equal to dx dy dz. And again, we can show that this is going to give us what we know the volume of a what do you call these? A volume of a rectangular prism is going to be. Okay. You can do the same thing to prove what the volume of a sphere is. And again, I'll leave that as an exercise for you to show that dv, if dv is equal to r dr sine of theta, this is r squared dr sine of theta d theta d phi, that when we do this integral in 3 dimensions, we end up finding that the volume of a sphere is the 4/3 pi r cubed that we know that it is. Okay. Now, the last thing that I want to do with this before I move on is to talk about how we can go back to the area under the curve, the familiar way that we see these things in our calculus class. And that's really going to be doing exactly the same thing that we're doing here. It's just going to affect what the boundaries are going to be. So consider some line, and we'll just do the simplest example, just some straight line y is equal to x, okay? And we want to find the area under this curve from 0 to some a, okay? So basically we're finding the area of this triangle. So before, when we did this in our calculus classes, what we said was, well, we can find the area of this by just plugging the function that I have in here into into an integral equation to say that this is going to be, this total area is going to be equal to the integral from x is equal to 0 to x is equal to a of x dx, right? That's exactly how we would have done this if this was a calculus class, right? Don't look at me like I'm telling you something you've never heard before, right? Yeah. Correct. Everybody knows. Okay, good. So how can we come back to this same conclusion by talking about these in terms of, really what we're doing here is we're doing Riemann sums, right? We're making all of these rectangles like this to find what this area is. But what I'm trying to show you here is you can do the same exact thing if I, instead of talking about these long rectangles, you use these tiny little boxes. So let's see how we can get this same thing to come back. So in this case, dA is going to be equal to some dx dy. And then when we plug this into our equation here, a is going to be equal to the integral of dx dy. And actually I'm going to reverse this. I'm going to do this dy dx. This is going to be a double integral because I have two variables of integration. Now, to get this to look like this, we need to consider where does y start and where does it end. So if I'm looking at this, where does y start? 0, right? So this is just going to be y is equal to 0. Where does it end? That's the tricky part here. Where does it end? Where does it go up to? It goes up to x, right? Because it goes up to this function here. It goes up to the line. And so this is going to go up to y is equal to x. How about x? Where does x go? X starts at 0, right? And it goes up to a, right? So this is going to be equal to a. So now let's do the first integral. First integral says the integral of dy from 0 to y is equal to x is just going to be x, right? And so we see a is equal to the integral of x is equal to 0 to x is equal to a times x dx. And this gives us back exactly what we would have expected that it should. Okay, it's just a slightly different way to think about it. Any questions about this? So again, the reason why I'm talking about these examples, they give you answers that you know they should because we're familiar with geometry. We know what the length of a line is. We know what the area of a square is. But it's getting to. I spelled different wrong. Different. That was good. Nobody wanted to spare me the. I appreciate sparing me the embarrassment of. But this is going to be on the internet forever now. So, okay. But this is really getting at this idea that I was talking about here. That a lot of the things that we're going to be doing in this class are thinking about how do we build integrals. And I think ultimately that's one of the big takeaways from what we're going to do is that integration is not just something that your math professor says, here's a list of integrals, do them. Integration is a way to think about how is it that I'm going to add up little pieces. And that's going to be something that we're going to see over and over again in the context of physics. Okay, any questions about this? Yeah?
For doing the second part of the integral, where you're integrating x, I'm a little confused about the lower bound. It seems like the lower bound is always moving up, like the lower
Right. So there was something that I swept under the rug here, and that has to do with the order that you're integrating the two things. So when you have, and it's a very good question, but it goes beyond the scope a little bit. When you have two variables that you're integrating over, you integrate out one of the variables when you do these. So the first thing that I did was I integrated out y. I got rid of it. So then the only thing that I'm concerned with is in terms of the numbers here, where is x going to go? But I could have done this the other way around, right? What I could have said was, well, rather than saying where does y start and where does y end, let me start by saying where does x start and where does x end, and then do the y afterwards. It ends up giving you the same answer. Okay, good question. Any other questions? Okay. Okay. So let me think. Where was I going next? Where was I going next? Vectors. Okay. So again, this is going to be primarily review. This is going to be primarily review. But I do want to talk about it because breaking vectors and components is going to be something that's going to be very important to be able to do in this class. So to start with, I want to introduce some notation here to talk about unit vectors. So when, just out of curiosity, when you took Physics 1, did you talk about unit vectors like x hat, y hat, r hat? You've seen, maybe some of you have seen this notation? Yeah? Okay. Okay, so this won't be completely new. So what this allows us to do is it allows us to talk about what direction something's going to point. So the unit vector x hat is just a label to tell you that something is going to be pointing in the x direction. Same thing with the unit vector y hat. It tells you something's pointing in the y direction. Now the unit vector r hat is a little bit trickier because in practice it can have both components in x and components in y. Right? So what we're going to need to be able to do is we're going to need to resolve what r hat is in components in x and in y. Okay, so if I give you just some angle theta here and I tell you this is some r hat, we know that r hat is going to be something in x plus something in y. So take a second and talk to your neighbor to figure out what this one's going to be. So what are you guys thinking?
I don't remember r hat.
Okay. Okay. So r hat is it's like pointing, right? So if there's something over there, r hat is just the vector that I'm pointing with at it. Okay. And in principle, that could be it could only be in x, it could only be in y, it could have parts in both x and y. And so what we're trying to do here is say that if I have some r hat that points like this, how much of it is in x and how much of it is in y. Does that clarify it? Okay, good. Okay, so let's go ahead and talk about this one. So what did we come up with here? What's the amount of r hat that's going to be in x? Cosine theta? Sine theta? I like tangent theta. That one's my favorite. It should be cosine, right? This is cosine. No, you can't. I mean, you can't just like throw things in there just because you like them, right? No, this has to be cosine, right? Because this portion, the x portion, is going to be the part that's adjacent, right? And we remember that the definition of cosine is going to be the adjacent divided by the hypotenuse, right? And here, the hypotenuse is going to be what? It's a unit vector. It's a very specific value for this. It's going to be the magnitude of r hat, right? What's the magnitude of r hat? I didn't quite talk about this. It goes back to something you might have learned last semester. 1, right? And that's a very important thing here. When we talk about unit vectors, I use notation r hat. That's different than r vector. R vector can have any length it wants. R hat can only have a length of 1, right? So when we're looking at this, we say that cosine is going to be the adjacent divided by the hypotenuse. That value of the hypotenuse is just going to be 1. So the cosine of theta is the adjacent. when we're talking about these unit vectors. Okay. How about y hat? What should y hat be? Sine, right? So this is just going to be, this is our cos theta, this is our sine theta, sine theta. And because a lot of people really like to just put equations in their bag and then call it a day, you might be inclined to say, okay, well, r hat is equal to cosine of theta x hat plus sine of theta y hat. That's what it always is. What's wrong with that? What could change this so that's not true? Yeah, there's a couple of things, right? If somebody said add a z, right? So I could do this in spherical coordinates. So there's something coming out here. That's a little more complicated than what we'll do. That is one thing you could do. Another thing was to change where the angle is, right? So here I'm measuring the angle relative to the positive x-axis, and if the angle is measured relative to the positive x-axis, yes, this is always going to be like this. So if I give you something like this, yeah, r hat is going to be cosine of theta x hat plus sine of theta y hat because the angle is measured relative to the positive x-axis. Okay, but that's not always convenient to do working with angles that are greater than 90 degrees. So let's do another example. Let's see what happens when I do this angle. Okay. So go ahead and talk to each other about this one, and let's see what this r hat is going to be. All right, so what do you guys think?
They would be switched. It'd be r hat equals sine theta x plus cosine theta y.
You're close.
Would one of them be negative?
Maybe. Think about why. Think about why. Where is this vector pointing, and where is the positive y-axis? Where is the positive x-axis? Is a question? No? Okay. So what do you guys think? What do you guys think? Right. Why is it negative sign?
You're using it from the left side.
Right. Right. So this is positive x. This is positive y, right? And this is going the opposite way. Exactly. Exactly. Good. Good. Okay. So let's go ahead and talk about this one. I heard a lot of good things here. So let's write this one down. R hat is going to be equal to some amount in x hat plus some amount in y hat. What is our amount in x hat? Negative sine of theta. Good. Why is it negative? Say again?
It's in quadrant 2 and x.
Yeah, it's in quadrant 2, which means that x is negative, right? So I could draw the two vectors that literally that's what we're doing here, right? When I find some unit vector like this, I'm adding the amount in x and I'm adding the amount in y, and the amount in y and the amount in x, and the amount in x is negative here, right? Because this is positive x-axis. How about our y hat? Cosine theta. Good. Good. So something else that you see here, and again why it's important to go through these individually, and I haven't taught the calc-based in a while, but something I see often with the algebra-based students, they like to say that the cosine is always the x part, right? Cosine's always x, sine's always y. Well, we see very clearly here that that's not the case, right? Sine and cosine could be the x or the y. It depends on what the angle is that we're given. Okay? Any questions about this one? Yeah?
So for the second quadrant, the way I know is that sine is always positive. Why do we have minus sine x? Is it because of the angle? Or? Okay,
right. So what I'm doing here. So I think what you're thinking about is this mnemonic. Some people say all students take calculus. The way that one of my friends in one of my algebra classes, the way that I remember this is the American Spicy Taco Club. But that's what you're getting at here, right? That if I treat it like this and I say, okay, well, is sine going to be positive or negative in which quadrant? Yeah, this is getting to that same idea. This is getting to the same idea here that sine is positive here. Well, actually, no, it's not really. No, it's not really. Let me think about how I want to explain this. Really, when we use this mnemonic, it's always the angle relative to the positive x-axis. Okay, and that's why I can say if I'm changing this angle and it comes over here, sine is going to be positive, but cosine is going to be negative. Right? If I get over here, tangent's going to be positive because it's a ratio of sine to cosine. Over here, cosine's positive. But the reason why this is negative is looking at this unit vector is going to be in the negative x direction. And we just put this negative sign in by hand when we look at it and say, okay, well, the component, the magnitude of the component is going to be the sign because that's the opposite portion. But the positive or negative sign I get here because it was in the negative x direction. Okay, does that clarify things? Okay, good. Any other questions about this? We'll get, when we get into Coulombs Law, we're going to get a lot of practice with this, but I want to kind of lay it out in general terms to start with. Okay, we're all good? Okay, so let's write down what Coulombs Law is and talk about what Coulombs Law means. And we might have a little bit of time to do an example. Okay, so what Coulomb's law tells you is what the force is between two charged particles. So consider, let's say we have some atom here. So we know that the nucleus is going to be positive and the electron that's going to go around this is going to be negative. And we can give these some labels. So we can say that the protons, or the collection of protons in the middle, can be some Q1. The electrons, or the single electron, is going to be Q2. And what we'd like to do here is we'd like to talk about what is the force between these two. We know from our previous experience, maybe watching Bill Nye or something, that positive charges attract negative charges, right? So opposites attract and likes repel. So if I had two positive charges, these would repel each other. Two negative charges, they would repel each other. So what we'd like to do is we'd like to talk about what the force is between these. And that gets us to what's called Coulomb's law. So what Coulomb's law says is that this force, and I'll break this down in more detail as I go, but this force that charge 1 acts on charge 2 is going to be equal to 1 over 4 pi epsilon naught times Q1, Q2 over R squared times R hat 1, 2. Okay. So let's talk in detail about what every part of this equation means. So the first part is the portion on the left. This is the force that charge 1 acts on charge 2. Okay, so the force that charge 1 acts on charge 2. Now this is a vector, which means it's going to have some direction associated with it. And something just to note, because I never want to see anybody ever do this. If you write a vector on the left side of the equation, you need a vector on the right side of the equation. It doesn't make any sense if you have some vector is equal to some scalar. So I have some f vector here, and I have an r hat on the right side of the equation to make this a vector is equal to a vector. Okay, let's look at the next part. This is a constant, 1 over 4 pi epsilon naught. Epsilon naught is what's called the permittivity. Check my spelling. I think that's how you spell it. The permittivity of free space. Okay. And we won't talk too much about what epsilon naught means now. Ultimately, it's related to the propagation of electric fields, and it comes partially because of how we measure things. So because we measure time in seconds, we measure length in meters. This has a particular value. Now, ultimately, one of the punchlines at the end of the semester is that this is related to the speed of light. And we're going to see exactly why that is when we get to the wave equation. But for now, when we're doing these calculations, this whole thing is just some constant. You just carry that around with you when you do the calculations. So let's talk about what Q1 and Q2 are. And why the way that I'm doing this is a little bit different than the way you might have seen it before if you'd taken a high school physics class. Q1 and Q2 are an amount of charge. And what that means is if I have a positive charge, I plug a positive charge in here. If I have a negative charge, I plug a negative charge in here. Okay, so those are the amount of charges. In this case, this would be identically this Q1 and identically this Q2. But I could say, for instance, this Q1 is equal to plus 3Q, and this Q2 is going to be equal to minus 2Q. Something like that. And then I would plug this 3Q in for Q1, I plug in the minus 2Q for Q2. R is just the distance between these, okay? So this is going to be the distance between these. So let's give this some distance of D. R hat 1, 2 is the unit vector that points from charge 1 to charge 2. And it's always the unit vector that points from charge 1 to charge 2, okay? So here, this unit vector, R hat 1, 2, is going to point like this. Okay, now if I give this, and I want to talk about why this is consistent with our expectations. If I put this on some x-axis here, let's go ahead and calculate what this force is. And so we've determined all of the things in this equation. We know that this R is going to be this distance D. This R hat 1, 2 in this case is going to be just some positive x hat, right? Make sense? So we found all of those things. Now, to find what this force that this acts on this, all we need to do is we need to plug everything into the equation. And so when we do that, this says that this is going to be 1 over 4 pi epsilon naught. Q1 is going to be this plus 3Q. Q2 is going to be minus 2Q. R is going to be D, we're going to square it, so this is D squared, and R12 is just going to be X hat, okay? Now we can multiply these together and simplify it a little bit, so let's actually start just by canceling a factor of 2 here. So there's a factor of 2 here, I can get rid of a factor of 2 in this denominator, and then rearranging this, what we end up seeing is that this is going to be minus 3Q squared over 2 pi epsilon naught D squared times X hat. And that is what F12 is going to be. Now let's go ahead and check and see if this is consistent with our expectations. We know that this is a positive charge and this is a negative charge. Should these be attracted or repelled from each other? Attracted, right? So this one should be pulled that way. Does this equation say that? Yeah, because the direction that this is going to be going is in the negative x direction. Okay. Who's seen Coulombs Law before? Have you've seen it in like a high school physics class? Yeah. So like I said, I'm going to be using a slightly different way of doing this than you might have seen before. And there's a good reason for that, because doing it this way is really the only way to do it when we talk about distributions of charge. So later what we're going to do is we're going to say, okay, instead of having just some point charge here, what happens if I take that charge and I stretch it out? So I have this charge spread over here, and then this charge over here. That's why I'm doing it this way. Now, if you've seen this before, what you might have done is you'd say, okay, well, let me just compute the magnitude of the force, and then in the end determine the direction based on whether these are going to be attracted or repelled because they're like sign or opposite sign. Here, the equation does all of the work for you. You just need to be careful when you use it. And when I plug the charges in here, I plug in exactly what the charge is. If it's positive, I plug in positive charge. If it's negative, I plug in a negative charge. And r hat 1, 2 is always going to be the vector that points from this one to this one. Okay. Well, we'll get a lot more practice with this, but I just kind of want to lay that out. Yeah.
When you were talking about, like, if that makes sense, which one are we determining is going to the left? I know it's supposed to be negative, so you have the -3 on there.
Right.
Are we looking at the
Yeah, okay, yes, okay. So, yeah, what you're asking is an interesting question. I think what it's getting to is which charge am I talking about the force acting on, right? I'm talking about the force that charge 1 acts on charge 2. So these are the things that are happening to charge 2.
So since our force is negative, it's pulling the negative towards the positive?
Exactly, exactly. And that kind of gets to what this notation means here. This is the force that charge 1 acts on charge 2. This is what's happening to charge 2. Now, we could talk about the opposite, right? We could talk about what the force that charge 2 acts on charge 1. And there's two different ways that we can think about this. There's one kind of easy way that we can just write down the answer right away. What did we learn last semester that would allow us to just write the answer down right away? Involves some old English dude that had long hair and had an apple fall on him. It's Newton, right? Yes, equal and opposite reactions, right? So if this charge acts a force on this one is going to act an equal and opposite force on this one. Okay. So what that means is that F12 is going to be equal to negative F21. Okay, so we could just write the answer down like that, or we could actually just go through the calculation and see exactly why that's the case. Okay, so we know what the diagram looks like. Okay, so let's actually just go through this calculation. And actually, now I actually do need this back. So this is going to be our plus charge was on the left. Yeah. This is okay. So this is Q1 is equal to plus 3Q, and then this is Q2 is equal to minus 2Q. And something I need to be cognizant. Can you guys read this in the back? It's okay. I'll try to make it a little bigger. So this is Q1 is equal to plus 3Q, and Q2 is equal to minus 2Q. It's better? Okay. So if we want to find the force that charge 2 acts on charge 1, there's really only one thing in this equation that's going to change, right? Q1 and Q2, when I plug these in, those are just going to be the same, right? And multiplication's commutative, right? What does that mean? What do I mean when I say multiplication's cumulative? Multiplication is commutative.
You can multiply in any order. It's fine.
Exactly. So that's to say, if I take 3 times 5, this is equal to 5 times 3, right? So the order that I multiply these in doesn't matter. But when we look at r hat 21. So this is the unit vector that points from charge 2 to charge 1. This is going to be in the negative x hat direction. And what we said before was r hat 12 is going to be equal to positive x hat, right? So what this says is that r hat 21 is equal to minus r hat 12. And this is, when we go through the calculation, exactly why this is the case. Okay? And you can go through these arguments, and the homework question's slightly more complicated than this, because for the homework question, it's not just on the axis here. I'm not going to do it for you, but I'm just going to talk about it quickly. I know everybody's disappointed I'm not doing the homework for you. So this is going to be some minus A, minus B. And then I think I put Q1 here and I put Q2 here. And we want to find what the force is between these two. So I'm actually going to end class a little bit early today because I don't want to start anything new. Make sure that you, so just generally speaking, in order to be successful in this class, go through the notes when you're going through the homework. And I posted videos that go through the calculation that I have, let me see, in the notes for the first two examples in the Coulombs Law section, and those will be really helpful for when you do this homework question. All right, so that's going to be it for today. I'll see you guys on Wednesday.